Hi again everyone, I'm Steph and I'm the General Math Lecturer, and today we're going to be reviewing the topic data and statistics. Okay, so the first thing we're going to be focusing on is the capture-recapture technique. So this technique is used to estimate population sizes when we actually don't know how many people or things are in this population. So it's helpful for questions when we need to find how many things are in a population. So to do this, we use the capture-recapture technique, and as you can see, I've written the steps here that you need to use this technique and solve for the population size. So the first step is use P to represent the population size. So in our first capture, we represent this by going the number of things captured or people captured or fish captured, wherever we're capturing, over P, which is the population, which is what we're trying to find. And in the second capture, we write the number recaptured from the first sample over the number captured in the second sample. And then the fourth step is to equate the two resulting fractions and put them side by side, and then we solve for P. So let's move on to a question that uses this formula. Okay, so the first question is, so the capture-recapture technique was used to estimate a population of seals in 2012. Okay, so we're using capture-recapture, and it was used to estimate population size of seals in 2012. 60 seals were caught, tagged, and released. Later, 120 seals were caught at random. 30 of these seals had been tagged. The estimated population of seals in 2012 was 11% less than the estimated population for 2008. What was the estimated population for 2008? All right, so the first thing we're going to do is write out what our estimated 2012 population was and find that out. So we know that in the question it says the estimated population of seals in 2012 was 11% less than the estimated population for 2008. So we need to find 2008, but first we need to find what 2012 was in order to work out what 2008 was. So our estimated 2012 population was, so we go the number of seals captured in the first capture over P and put that equal to the number recaptured from the first capture over the number captured in the second sample. So that was 120. So we just solve for P here. So all we can do now is just move P to that side. So we get 60 equals 30p over 120 times both sides by 120. So 7,200 equals 30p. Divide by 30 on both sides, and we get P equals 240. Okay, so we know that, this is 2012's population, right? But we know that 2012 was 11% less than the estimated population for 2008. So if 100% is 2008, then 2012 is going to be 100% minus 11%, which is 89%. So that's 2012. So basically, 89% of 2008's population was equal to 2012's population, which was 240. Okay, so now we need to work out what 100% was, or is. So, to do that, we can use the unitary method. So 89% equals 240 divide both sides by 89. 1% is equal to 240 over 89. Just leave it as a fraction, that's fine. Times both sides by 100 to get 100%. So 100% equals 269.66, which is 270 to the nearest whole number. Obviously, it has to be a whole number because we're dealing with seals, and we can't have 0.66 of a seal. So nearest whole number. Sorry guys, a bit squishy, but yeah, that's that one. So I'll just highlight that answer for my marker. Okay, so therefore the population for 2008 was 270, or the estimated population. Okay, so now we're going to be looking at normal distribution. So there's some things we're going to go through before we actually go onto the questions. So we should know that the standard deviation is a measure of how far away a score is from the mean. And then the mean is the average score. Okay, so question 2. A machine produces nails. When the machine is set correctly, the length of the nails are normally distributed with a mean of 6.000 centimetres and a standard deviation of 0.040 centimetres. To confirm the setting of the machine, 3 nails are randomly selected. In one sample, the lengths are 5.950, 5.983, and 6.140. The setting of the machine needs to be checked when the lengths of 2 or more nails in a sample lie more than 1 standard deviation from the mean. Does the setting on the machine need to be checked? Justify your answer with suitable calculations. Okay, so we know that the mean is 6 centimetres. Okay, so let's just underline that. And the standard deviation is 0.040. And basically, this machine needs to be checked when the length of a nail is more than 1 standard deviation from the mean. Or, sorry, when 2 or more nails in the sample are more than 1 standard deviation. Okay, so basically we need to find how far away these nail lengths, so these ones here, how far away they are from the mean of 6 centimetres. So if they're more than 0.040 centimetres, if they're more than that, then this machine needs to be checked. So if 2 or more of those nails are more than 0.040 centimetres, it needs to be checked. All right, so basically we're going to take each measurement and plus or minus 6 to it. Okay, so let's take the first one, 5.950. So because it's less than 6, I'm just going to minus it from 6.000, minus 5.950. And this will tell us how far it is away from the mean. So it's 0.050. Okay, so that number there is more than 0.040. So it's more than 1 standard deviation from the mean. So we'll just put here outside range. Okay, let's take the second number. So this can be 5.983. So I'm going to do exactly the same as what I did in the previous part. So 5.983. So we put that into our calculator, we get 0.017, which is less, this is less than 0.040. So it's not outside 1 standard deviation from the mean, so it's in range. Okay, so let's try our last measurement. So 6.140 minus 6.000 is equal to 0.140, right? So this is more than 0.040. So it's outside the range. Okay, so the question wants us to answer if the setting on the machine needs to be checked. So, and we know that if 2 or more nails lie more than 1 standard deviation from the mean, the machine needs to be checked. We have 2 that are outside the range. So therefore, 2 nails lie outside 1 standard deviation from mean. So therefore, the machine needs to be checked. Okay. So another thing that we're going to be working on today is interpreting sets of data. So the first thing we're going to be looking at is box and whisker plots. So we should know how to interpret box and whisker plots, draw box and whisker plots. So this is on your formula sheet, but I thought we'd just go over it anyway. So we know the lower extreme and the upper extreme are the lowest and highest scores. Q1 is the bottom, represents the bottom 25% of scores. Q2 represents our median, which is 50% of scores. And Q3 is the top 25% of scores. And another thing to note is the interquartile range is Q3 minus Q1. So that's how we find the interquartile range, and this is also on your formula sheet. Okay, so we should know how to identify when a box and whisker plot or a set of data is positively skewed, negatively skewed, or normally distributed. Basically, when you have your box and whisker plot, the Q2, when Q2 is to the left, it's like skewed to the left, you could say that your data is positively skewed. And when the median, Q2, is to the right, you could say that your data is negatively skewed. So it's really important to just memorize these 2 points. So when your data is more pushed to the right, like your median is pushed to the right, that means it's negatively skewed. And when it's to the left, positively skewed. Okay, so the graph showed the distribution of the ages of children in Numbertown in 2000 and 2010. Okay, cool. In 2000, there were 1,750 children aged 0 to 18. How many children were aged 12 to 18 in 2000? Okay, so the first thing we're going to look at is, let's just draw this here. So in 2000, the whole population of 0 to 18-year-olds was 1,750. So this whole line here represents 1,750 children. So we need to find how many children were aged 12 to 18 in 2000. So 12 to 18 is from here, our median, because we know this is 50% of scores, to here. So this is age 12 to 18. So basically all we do is find 50%, so half of 1,752. So we know that 100% of children in 2000 was 1,750. So therefore 50% would be 875. So therefore 875 children were aged 12 to 18 in 2000. The number of children aged 12 to 18 is the same in both 2000 and 2010. How many children aged 0 to 18 years are there in 2010? Okay, so from our previous question, we know that here and here represents 875 children. And it's the same for here to here. This is also representative of 875 children. So we know that this part of our box and whisker plot represents 25%, because here is 50%. So from here to here is 25%. So we can say that 25% of children in 2010 is 875, right? So then we want to find 100%. So we want to know 0 to 18 years. So therefore, 100% would just be times that by 4, because 25 times by 4 equals 100. So 875 times by 4 is 3,500 children. Okay, part 3. Identify 2 changes in the distribution of ages between 2000 and 2010. In your answer, refer to measures of location or spread or the shape of the distributions. So we know the shape of the distributions is referring to skewness. And then we can also talk about, in measures of location and spread, we can talk about median, interquartile range, any location measure that you can think of. Okay, so from 2000 to 2010, let's look at the median. So the median is here, right? Here and here. So we can see that from 2000 to 2010, the median has decreased from 12 to 6. So that's 1 point. Okay, another point we can look at is the skewness. So that relates to the shape of the distributions. So if we look at 2000, our box and whisker plot is relatively to the right. And then in 2010, it's relatively to the left. So we can say that in skewness, it has changed from negatively skewed to positively skewed. So changed from negatively skewed to positively skewed. Okay, so the last part of this question is, what would be one possible implication for government planning as a consequence of this change in the distribution of ages? Okay, so as you can see in 2010, we have a lot more children in the 2 to 12 range. So if you know children very well, they love going to the park, they love going to playgrounds, skate parks, and children from 2 to 5 also attend preschool. So one possible implication for government planning would be that we would need more government funding for playgrounds, skate parks. And by the way, in this question, you can pretty much make up anything that sounds reasonable. Okay, so playgrounds, skate parks, and preschool facilities. As as more children are aged 2 to 12. Okay, so that brings us to the end of this video. If you have any more questions relating to data and statistics or any other math topic, please head over to our Mathematics General 2 forum on our website, and we'll be happy to help you out, answer any questions that you have. And also, I highly recommend that you check out our Mathematics General 2 course notes that are located in our shop. These notes are highly detailed and have loads of practice questions for each topic in the course and detailed work solutions for each question. So I highly recommend that you guys check them out, and I hope you enjoy the rest of your day.